Okay, well, welcome everyone back to our session on physical science, adaptation and resilience, current risks, early warning systems and adaptation finance. In the morning, we had a panel discussion following a set of talks, and this afternoon, we're going to hear from a very small sample of our submitted poster presentations. So these presentations were selected really to represent the big sort of diversity of posters that were submitted to the session. And I would really encourage you also to go to the poster gallery, where you'll see lots of really interesting posters made by other people on this topic. And so the overall aims of our session are to elucidate the role that particularly robust early warning plays in adapting to climate change via disaster risk reduction and financial services. And our posters we're looking at today, they are looking at sort of scientific progress, the connections between functional early warning and functional early warning and accurate risk assessment, and then finally novel financial instruments that utilise the state of the art for risk assessment. So I'm going to now hand over for a series of short presentations from our presenters this afternoon, and after each presentation there will be an opportunity for the presenters will address some questions. So please do put your questions in the chat as soon as you can. I mean, not in the chat, in the form as soon as you can. And then at the end, we'll have time to pick up any questions which we didn't quite get to in the session after the talks, but also maybe some more general points as well. So I'm going to share my screen now, which will have these posters on them. So you should be able to see now the posters. So up first is Raquel.
Hi, good morning, good afternoon or good evening, everyone. So the study I'm going to present is part of a bigger study that is looking at the interconnections between assets, vulnerability, resilience, and adaptation to extreme temperatures. Emily, could you share the poster, please? Thank you very much. So the frequency and intensity of extreme temperature events are increasing, imposing greater impacts on human health and well-being over time. Many have called for a better understanding of the factors and processes contributing to human resilience, as well as policies to improve resilience. Some international studies suggest that access to and availability of assets play a determinant role on resilience of individuals in adapting to climate change. Definitions of resilience vary greatly, and this was one of the topics that was addressed in the morning, and it can mean a lot of things to a lot of people. In this study, resilience is defined as the ability or capacity of individuals to respond to challenging life events or threats through actively accessing, mobilizing, and using the available assets to positively adapt. It is a function of the ability to make sense of threats, the availability of and access to assets, and the motivation to respond to threats. General resilience is defined as the resilience of individuals to all daily life circumstances, and specified resilience is defined as the resilience of individuals to a particular type of threat. This study aims to respond to the complex interactions between extreme temperatures, resilience, health, and well-being, and provides an interdisciplinary approach to explore and understand the multiple factors that shape general and specified resilience using an asset-based approach. Research is needed on the resilience of human population to extreme events and the factors that increase resilience. Improving the resilience of the most vulnerable individuals has also been advocated, but the lack of evidence on the determinants of human resilience to extreme temperatures is considered a major gap in knowledge. The aim of this study is to investigate the general and specified resilience of individuals to extreme heat and extreme cold temperatures. It uses an interseasonal, multidisciplinary approach, as well as an interseasonal mixed methods approach. It's a case study of Lisbon in Portugal. And it also uses a new theoretical and analytical approach to assess general resilience, which was developed using the sense of coherence scale in order to construct the General Resilience Index, the GRI, using a composite index approach. The GRI includes the sense of coherence, three indicators of comprehensibility, manageability, and meaningfulness. The development of a GRI is novel and contrasts with other literature that investigates resilience as an overall static capacity of individuals. The advantages of using the GRI is that it allows explorations of the factors shaping general resilience. Additionally, it can also be adapted to other threats, which constitute a broader contribution of this study. The development of such an index has a huge potential, as results could be easily comparable within and between studies. Qualitative data is also used to assess individual participants' levels of specified resilience to extreme temperatures. Each participant's interview's data were analyzed, and the three dimensions of resilience were coded as high or low using thematic analysis. As you can see on the poster, the majority of participants were high on the three dimensions of general resilience and general resilience index. The themes of specified resilience were organized around the three dimensions of resilience and reflect resilience characteristics in terms of cognitive, comprehensibility, instrumental or behavioral, manageability, and motivational, meaningfulness features when dealing with extreme temperatures. Many of the themes were similar to both extreme temperatures. Despite this, some differences were found that relate to the levels of predictability that were lower for cold than heat. Availability of assets was found to be higher for heat than cold, and availability of strategies to deal with cold lower than heat. The majority of participants revealed high heat-related comprehensibility, followed by high meaningfulness and high manageability. Overall, the majority of participants revealed high heat-related resilience. These findings suggest that most participants viewed heat as being predictable and explicable, with which they had assets available to deal with and to which they invested their efforts in order to be able to respond. The majority of participants revealed high cold-related comprehensibility, and half of participants revealed high meaningfulness. Fewer participants revealed high manageability, and the majority revealed low cold-related resilience. Profiles or storylines of resilience of individual participants were also developed to bring to life individual characteristics, as each participant represents a unique pool of resilience characteristics that can be underrepresented when looking at the overall sample data. So in conclusion, resilience policy and strategies could focus on improvements in physical assets, such as home insulation and provision of cooling and heating. Also financial assets, such as reduction of gas and electricity bills, social assets, such as social activities to improve social networks, and place-based assets for better access to public green and blue spaces for cooling and public indoor spaces for cooling and heating. Concrete policy recommendations could take the form of programs, plans, and actions supporting individuals to better deal with challenging life events through people or community-centered approaches and delivered locally. Prospects for linking resilience and adaptation to extreme temperatures also exist through links with the United Nations 2030 Agenda for Sustainable Development, and opportunities for further research might include investigating the resilience of individuals and communities to different threats, such as wildfires, drought, and floods in different locations. Thank you very much.
Thank you very much, Raquel. That's really fascinating. We haven't had questions come through yet, probably at the end. So we'll move straight on to the next presenter, who is Lauro. from CIMA Research Foundation is going to present on present and future country risk profiles for floods and droughts in sub-Saharan Africa. So I'm just going to go onto the poster now.
Thank you very much. Good morning, good afternoon, good evening, wherever you are. My name is Lauro Rossi and I'm Program Director at CIMA Research Foundation, Italy. Today, I would like to talk about the fully probabilistic risk assessment for floods and drought that was carried out in 16 countries in Sub-Saharan Africa. This was part of the ACP program called Building Disaster Resilience to Natural Hazard in Sub-Saharan Africa regions, countries, and communities, financed by the European Union through the United Nations Office for Disaster Risk Reduction. We know that climate change affects the extreme of hydrological cycles following diverse patterns across the African continent. So this pattern must be investigated and understood to really quantify impacts on human life and economic losses on sustainable development. To this end, a state-of-the-art fully probabilistic risk assessor framework was implemented to understand the probability that different magnitudes of flood and drought event will occur over an extended period of time. This complex modeling framework is composed by several models that are here represented at the top left as bubble, interconnected to each other. Present and projected climate condition of RCP 8.5 were used to drive a fully distributed hydrological model to compute present and projected hydrological stream the flood impact modeling change considers hydraulics, topographic property of the channel and flood plains, flood protection, and vulnerability exposed assets. Drought impacts were computed in terms of potentially affected people and livestock, impacts on hydropower production, and impacts on crop production. This modeling framework was then used to simulate thousands and thousands of scenarios, which provides the statistical basis for economic loss metrics such as average annual loss, AAL, probable maximal loss curve, which gives a measure of the economic losses as function of the return period. I just want to show you a couple of examples of these type of results that are reported here at the top right. The map represents a variation of flood and drought risk in these 16 countries. For example, if we take Zambia, we observe an increase in both drought and flood losses in projected climate. This is evident in terms of both average annual loss and PML curves. In Angola, we have similar situation for drought risk, while flood risk does not seem to increase if we only consider AAL. However, if we analyze in detail the PML curve, we realize that there is a huge difference in how losses will be distributed in frequency, with a tremendous increase of those events with low probability and high severity that can have a disruptive impact at country level. And this is my first takeaway message. We need a complete modeling framework that considers the full spectrum of interaction. And we also need a probabilistic approach to explore all possible independent scenarios. Results are presented at national, province, and in some cases, district level, and are disaggregated by sectors such as agriculture, housing, transportation, health, education, energy, and service. This modeling framework also enables some tests of drought adaptation measures, such as drought-tolerant crops or short cycle crops to investigate potential improvement in production and subsequent economic savings. And here we have an example for beans in Tanzania. And then my last point is about how socioeconomic development, and in particular population growth, will contribute to future risk. So affected population in projected climate conditions computed with both current and population distribution, which we know is unrealistic, and future population distribution. The idea was to investigate the contribution of only climate change on one side and the contribution of climate change plus population growth on the other. The results are often impressive, showing that the contribution of population growth could be even greater than the one due to climate change. So along with this quantitative result, a guidance document was developed to give an overview of the possible application of country risk profile and possible disaster risk reduction policies. This documentation has the aim of guiding and inspiring the policymakers towards the best use of probabilistic risk information. Thank you.
Great. Thank you very much. Have we got any questions yet in the spreadsheet? No. Okay, we haven't got any questions yet in the spreadsheet. So we'll carry on to the next speaker. So that'll be Gianpaolo.
Okay. So shall I start? First of all, I'd like to say I'm thrilled to present here today in the Adaptation and Resilience session. So I'm Gianpaolo Balsamo. I'm with the European Center for Medium Range Weather Forecast in the research department. And today in my poster, I would like to guide you through a journey that the center has started about a decade ago, moving from weather forecasting to prediction of multiple risk through thanks also to the associated services that this NWF is running. So my poster, if you can go to next slide, Emily. My poster is organized in different sessions. So first of all, in the introduction, I'll mention that the classical weather forecasting, so ECNWF, as many knows, is the world leader in terms of medium range weather forecast. So from few days ahead to several weeks, so going into sub-seasonal to seasonal forecasting. And it has been a journey to improve the different modeling system and embracing what we call the Earth system approach. So which consists of integrating in the forecast system through data simulation, several of the components, both the modeling and the Earth observation that characterize the ocean, the land, and the atmosphere, and embed that into an ensemble modeling system, which make use of both satellite observation and in situ and conventional observation. So you see here, for instance, in the sketch, the ocean waves and ice modeling component, which enabled the classical weather forecasting to take into account much more precisely what is the state of the ocean. And by that, we mean really the 3D ocean and it's at depth. And the state of the sea and the ocean waves, so being able to characterize waves height and risk to navigation, and the sea ice, both the concentration and the depth. All these components have been progressively included in the forecast, and now they are, each forecast that ECNWF issue has now an interactive ocean since June 2018. Similarly, the land component has been evolving to have a better account of the land hydrology, biosphere, and also what we call the anthroposphere. So, for instance, by introduction of urban tile and a urban model, which is able to define and produce some of the effect that cities produce on high temperature. So we have heard in previous talk the accent on the extremes temperature, and cities do modulate temperatures and are exposed to higher temperature in presence of heat wave. A particular focus in the poster is the effort that has been devoted to improve the CO2 modeling. And the reason that has been done is really to be able to produce, thanks to the Earth system approach and the high resolution of accuracy of the system, to have a CO2 monitoring and verification support capacity for instance, that can be useful in the implementation of the Paris Agreement. How that has been done, so there is a pathway to the improvement of the biosphere modeling by considering progressively more complex and better adapted parameterization, considering satellite observation that can constrain model error, and also simulating the human activity CO2 by, for instance, introducing the IPCC inventories, which are gridded and prepared on the model to characterize what are the main CO2 emissions for anthropogenic sources, so energy production, manufacturing, settlement, aviation, ground transportation, and other sources. All that you can see is plotted in the bottom left, gives us the possibility of representing also the CO2 emission for anthropogenic sources. The Earth system approach is using ensembles, meaning that several realizations are of the same model integration are produced over time, and this allows to characterize both for the weather, the climate, and the environment probability of occurrence of a given event. So this probability of occurrence, for instance, in case of extreme events like tropical cyclone or a heat wave, enable to support risk-based analysis, because you will have, for a given date and forecast range, you will have an idea of quantitatively how probable is this event. This system has been particularly useful in the Copernicus services, for which ECNWF is an entrusted entity for the Copernicus Climate Change and Atmospheric Monitoring Service. In the future, the Copernicus CO2 project, currently in a prototype phase, will add also the capacity of monitoring CO2, and in particular for the focus of providing the European Commission and the nation a monitoring verification support for the Paris Agreement. Another important initiative, which is going to shape a little bit the advantage of high resolution in the next 10 years, is the Destination Earth program. So this initiative is enhancing the computing and digital infrastructure to enhance what we call a digital twin of the planet. So we often say in climate change, there is no planet B, but actually a digital replica of the planet is a possibility from enhanced computing and more accurate modeling, which is going into the kilometer scale. So building on the experience of the European Copernicus services and tapping into the possibility of this new initiative to build the digital twin of the planet, the weather forecasting is really evolving towards a more complete treatment of the Earth system, using innovation in the computing and digital services that can really enhance the safety for life and livelihood. So, and this is with particular emphasis to environmental, weather, and climate extreme events, and also extending towards the assessment of how effective will be some of the green transition policy. This is one of the ambition of the Destination Earth. So, in conclusion, in the poster, the outlook of the how the direction towards 2030 will look like. A computer-based Earth system prediction may better support decision-making. This way, we are convinced that science-based decision-making can reduce and manage risk using the experience that comes from weather forecasting and climate reanalysis, such as ERA 5, for instance, in the Copernicus services. Computer-based weather models are evolving towards kilometer scale. So currently, the highest resolution ECNWF runs is a 9-kilometer global for its high resolution system and 18 kilometers for the ensemble. This is likely to go into a single-digit kilometer scale, so towards 1 kilometer in the next decade. A service-based Earth system modeling and data simulation using Earth observation and the ECNWF support, for instance, what's coming from the Copernicus services, can really enhance further the digital infrastructure thanks to Destination Earth. This is a cooperative project run by the European Commission in collaboration with the European Space Agencies, EUMETSAT and ECNWF. And it's a large project that will involve several of the member states and actors. So Thank you very much for listening to my poster.
Thank you. So I don't think we have any actual questions coming through from our audience. So if people could remember that do feel free to ask questions within the form, which is below the video, and don't try and ask them anywhere else, like within the poster gallery or something. Actually ask them on that form, and then we can put those forward for you. But if we haven't got any actual questions yet, we'll move on. Okay, then, great. So I think Graham is up next, and Graham is really great to have Graham here, because Graham doesn't come from an academic institution, but rather from Mott MacDonald, which is one of the leading scientific consultancy organisations. So it's really good to have that different viewpoint within our session. So over to Graham.
Hiya, thank you. So yeah, good afternoon, good morning, and good evening to everyone attending. As you can see from the title of my poster, I will be looking at the sort of impacts of hydraulic fracturing on future water demands and stress within Scotland. So yeah, as mentioned, I'm an environmental consultant with Mott MacDonald, but my sort of background before that was I did petroleum geology at university as my undergraduate degree. I then went on to study environmental management and sustainability for my master's, and that's where I undertook sort of the beginning of this research. So it kind of combined my undergraduate sort of interest in sort of petroleum and then the sort of more environmental sustainability aspects of it as well a bit later on. So we'll just jump in now to the poster sort of talk. So the recent water crisis in South Africa and Australia, as well as other nations all across the world, has highlighted the effect that water scarcity can have. Hydraulic fracturing opportunities in Scotland have been explored in the past, most recently sort of in the 2010s, where the map within the poster shows the study area that was carried out by British Geological Society and the Department of Energy and Climate Change. And the area that they really focused in on was the Carboniferous Midland Valley of Scotland. And that's the area where they found would have the highest prospective sort of shale gas availability. And it is crucial to sort of think about how much water would be required for a practice like hydraulic fracturing. A lot of research in the past has looked at the quality of water that would need to be required, because a lot of sort of research has gone into could seawater be used as a potential way of sort of supplying the water. But it's quite difficult because the water required for the process needs to be potable, which means it needs to be clean, it needs to be treated, which really does make it quite challenging. And it also needs to be able to cope with the growing population across the world and in Scotland. It needs to be able to cope with climate change and also the growing rise in demand for water. So the aim of my research was to quantify the water impact of fracking in Scotland and assess how climate change will influence water availability between 2020 and 2080. So I'll quickly move on now and just give you a very high-level overview of what hydraulic fracturing actually is. So it's often referred to as fracking, which is probably what everyone's more common sort of name for it is. And it's a technique used to extract oil and gas from low permeability rocks, such as shale and sandstone. The process typically involves injecting water, sand, and chemicals under high pressure into bedrock formation via a well, as the image on my poster shows. It is an activity that requires an abundance of water, with a typical well requiring between 10 and 20 megalitres of potable water. And to give it a bit of context, what a megalitre is, 1 megalitre equates to about 1 million litres. The British Geological Survey and the Department of Energy and Climate Change estimate there is up to 134.6 trillion cubic feet of shale gas within the Carboniferous Midland Valley. So that's quite a lot of gas available, which means if it ever was to be fracked, we would need a lot of water to sort of undertake this process. So I'll quickly now move on to talk about how we would potentially supply that water if this was ever considered in Scotland. So the availability of water through the supply network is variable across Scotland. the map on my poster here on the bottom left shows dots all across Scotland, and every dot represents a water resource zone. And basically what that means is for that one dot on the map supplies the sort of domestic and industrial water availability per day to that region. And in the central belt, there is good connectivity. However, there are supply zones that are vulnerable to drought risk, for example, Tayside and Ayrshire, as alternative supply options are currently limited. As I said, the water used in hydraulic fracturing needs to be treated. This research assumed then that Scottish Water would supply the water through the supply network. This would require domestic tap water being backworked through the system to a reservoir owned by Scottish Water. This will ensure that the water for fracking is supplied in a treated, potable manner, having been through the filtration process of Scottish Water. And when I did this research, Scottish Water very kindly presented me with all of the data for every single supply zone within this map. And that included how much water was there on a daily basis and what the raw water demand was on a daily basis for each region. I then narrowed those water resource zones down to 6 different zones. So I chose Glasgow, Perth, Fife, Edinburgh, Forth Valley, and Lanarkshire. These were the areas in Scotland that had the most water on a daily basis, and they were also quite appropriately situated quite close to the Midland Valley of Scotland. However, I did also look at other options on how this water could be supplied. I looked at, you could potentially just drain Loch Ness, and you could just take all the water out of there, and then you'd have all your water required for the next 30 years of fracking. But I didn't think that would go down too well with the Scottish Tourism Board, so we quickly moved on from that option. But yeah, so basically I've now sort of got 6 water resource zones that I'm going to evaluate. And it's important when we do this that we look at the impacts of climate change when doing this, because water availability today might not be the same as water availability in 60 years' time, per se, in 2080. So the UK climate change projects indicate that the average winter precipitation will increase in Scotland over the next century. By 2080, you could be looking at over 20% more water on a daily basis in Scotland. However, in the summer, the average precipitation will decrease significantly. So what this means is that we'll have much wetter winters, but much drier summers. But quite interestingly is that annually, the precipitation levels in Scotland won't actually change that much. There's only a 1 or 2% swing between now and 2080. However, it's going to be much more significant sort of seasonally. So it might be that we've got lots of water in winter, but it might be in summer we don't have as much. It's really about how we manage this resource moving forward. In addition to varying rainfall patterns, it is anticipated that Scotland's average annual temperature will increase over the next century. So basically, we've now got our 6 water resource zones. We've got a fluctuating rainfall pattern moving forward. And now we need to sort of put into perspective what the water demands of hydraulic fracturing would actually look like in Scotland. So as I said, the volume of water required per well ranges between 10 and 20 megalitres, with the average being 17 megalitres for the Marcellus Shale, which is a shale based in America. And that shale has been found to be one of the most comparable shales to the shales observed in Scotland. If operations within the carbonous Midland Valley of Scotland are similar to that of the Marcellus Shale in Pennsylvania, production could see an average of 2 wells being fracked per day. So I've quickly got a graph here, or a table, should I say, and basically I've split it into 3 different water scenarios. So the best case scenario would be 10 megalitres of water per well. The sort of most likely would be 17 megalitres per well. And the high scenario would be 20 megalitres per well. And if we were doing 2 wells per day, that could be 24 megalitres, 40 megalitres, or 48 megalitres. So that is quite a lot of water. And basically, I applied these results to each of the water resource zones. So I added the varying precipitation levels to the today levels.
Graham, can you start to wrap up, please?
Yep, that's fine. But basically the results of the presentation showed that 4 of the 6 water resource zones failed a water stress test, which means they didn't have enough water to supply the daily requirements, including hydraulic fracturing, domestic use, industrial use, and only Perth had the availability to supply the water demands for fracking and daily use in summer and in winter. But yeah, I will quickly wrap up there, but it just shows the importance of managing our water resources and potentially finding different solutions to providing energy across Scotland. But yeah, if you've got any questions or want to talk more, just drop me a message. Thank you.
Thank you very much, Graham. I think in the interest of time, we'll move straight on to our next speaker, who is Daniela.
Yeah, thanks. Good morning, everybody, and thanks for the chance of presenting this work. I currently work at the University of Southampton, and the work I'm presenting today is within a context of a much that it's called break, and it's now coming to the final year. The aim of the project is to look on Sub-Saharan Africa and understand how to improve water and food security. So the work I'm presenting today is within the analysis of whether remote sensing datasets can be used to inform weather index-based insurances. So here I'm just starting with very basic information about what a weather index-based insurance is, just to get everybody on the same page, although I know that most of you would be familiar with this concept. So these insurances are a financial tool that can be used as a risk coping mechanism for various fields, but especially for rain-fed agriculture. So the difference with respect to traditional insurance is that traditional insurance links the payoff to the actual damage experienced by the farmers. The weather insurance links the payoff to a weather index, which is supposed to be a proxy of the damage. Gauge-based precipitation is commonly adopted to define this index, but this has, of course, many advantages, but it has also an disadvantage, especially in data-scarce regions, is that it limits the spatial coverage of the insurance application. So the research question we address in this work are, can remote sensing compensate for scarce ground stations? Which weather indexes in this case can be best to represent the exposure of rain-fed maize to water scarcity? And finally, is there an added value in considering hydrological and vegetation indexes, hydrological variables and vegetation indexes instead of precipitation? Because of course, they can be more closely related to yield. Okay, so what we did is that we took a series of remote sensing data sets and we analyzed the spatial and temporal correlation between them and with some historical data of maize yield, focusing on Malawi. So basically, we analyzed one variable for each of the compartments we were interested into. So precipitation for meteorology, soil moisture for representing the hydrological compartment, NDVI and EVI for representing the vegetation health. And then we use historical data, historical records of maize yield from the official statistics of the Ministry of Agriculture. And these are per district. So on figure 1, you can see a map of how the harvesting of maize is distributed in Malawi. So most of it, it's represented with the darkest green color. So most of the maize is actually grown in central and south Malawi. And in figure 2, so you can see how is the time series of the national average of maize yield from the 80s to 2016. You can clearly recognize a step change in the mean of the maize yield. at the national level starting from 2006, and this is due to the implementation of some incentives for fertilizers and specific seed types that the government put in place after the food crisis of 2005, which was indeed caused by weather-related events, so a combination of unfortunate floods and droughts. So in the interest of time, I will move towards the conclusions of this work. So I listed here 5 main points that I wanted to share with you. So first of all, remote sensing data can capture the propagation of water stress or water availability, if you like, through the different compartment and time through the maize growing season, and can be used to inform potential indexes for weather index-based insurances. So the numbers there in the table represent the average Pearson correlation coefficients with of the different variables with the harvest, the maize yield, and they are not that high. Okay, so you can also see this can be due to various reasons. I will talk about this in a minute. You can also see that hydrological variables and vegetation indexes are not more effective than precipitation as a yield proxy. However, this picture is really location dependent. So the crop-water relationship depends on the location, and different districts may correlate better with different indexes. Generally speaking, standardized anomaly precipitation in March shows the highest and most spatially consistent correlation across Malawi. So what you see in figure 4 is a scatter plot between the CHIRP standardized anomaly in March and the yield standardized anomaly in central Malawi. So every point there represents a different year of the horizon we are considering and a different district. And as you can see, both high precipitation and low precipitation are generally correlated with low yield because they both produce water stress. But what is interesting to notice is that there is like a relatively big spread, especially for slightly below average precipitations. This is due to the fact that not only water stress can impact on the yield, but also many other aspects, like in particular factors that are not necessarily water related, like management practices. So we are now exploring what are these factors that may compensate for a reduced precipitation. Thank you for your time, and thank you.
Thank you very much, Daniela. It's really interesting. Index insurance is a topic which is close to my heart. I've done a lot of it in Thamsat. Okay, we're starting to get some questions coming through, but they're kind of lagged to the other talk. So I think we'll just press on for now, and then we'll come back to some questions at the end. Let me just so Annika's up next.
Hey. Yeah, hi, my name is Annika Stechemesser. I'm from Potsdam Institute for Climate Impact Research, and today I'm going to talk about the relationship between temperature and digital hate. So if you could go to the next slide, you can see my poster. So yes, evidence for a connection between human conflict and temperature has actually already been found in a number of studies. But these days, conflicts are not really limited to the physical space anymore. And racially offensive and discriminatory language on the internet, which is often referred to as cyber racism or cyber xenophobia, has become a prevalent problem in our digital age. And my co-authors and I examine in this study that I present here the effect of temperature on the occurrence and acceptance of racist, xenophobic, and religiously discriminating posts on the social media platform Twitter in Europe. So Twitter is actually still one of the most commonly used social media platforms and has more than 300 million active users worldwide, which makes it quite suitable for a representative analysis of online discourse. And our specific approach consists of combining Twitter data from European countries, which span multiple climate zones, with temperature data to assess the influence of temperature on the amount and acceptance of racist tweets. To that extent, we first have to identify some of these tweets. And we do that for the years 2012 to 2018. And we use a simple bag of words approach, which basically means that a set of keywords is assembled in each language. And then all tweets that contain any of these keywords are added to the dataset. Here we do not necessarily use the same keywords for each country, but we tailor our selection to the linguistic and cultural specifics of the language, and we do that with the help of native speakers. In addition to slurs themselves, we also include expressions that are composed from multiple words that only become offensive in combination. So for example, the words refugee and lazy themselves are not offensive words, but if you put them together in a certain way, they become quite offensive. Right. So when we have assembled the data, they then undergo a series of pre-processing steps until we finally apply a bin panel regression fixed effects model. And in that model, population-weighted daily maximum temperature is the independent variable, and the daily number of racist tweets and likes is the dependent variable. Specifically, we also include country and season fixed effects and controls for various things like precipitation or weekdays. And the results of this regression then show a quasi-quadratic nonlinear relationship between daily maximum temperature and the number of racist tweets and likes. And you can see this here in figure 1. And the levels of racist tweets, as we can see, are comparatively low in the 3 bins encompassing 8 degrees Celsius to 17 degrees Celsius, and then sharply increase outside of this temperature range. And in this window, the temperature dependence is so weak that we cannot detect it within our level of uncertainty. We then conducted like a whole number of robustness checks on like bin width and varying other things. But all the fits that were yielded, they had the minimum in the same window. And we subsequently defined this range of 8 degrees Celsius to 17 degrees Celsius as the climate comfort zone. To then build further evidence that the climate comfort zone is actually connected to a low number of racist tweets and likes, we conducted additional analyses at the country level for 3 countries that were also included in the European panel that have a high enough data density to allow an insightful and robust application of this statistical methods if the data set is limited to just that share. So here we employed Norway, the Germany and Austria region, and Italy. And these also all cover different climatic zones. For each country, we then compute a country-specific temperature racist tweets response function, which is shown in figure 2. And as you can see, all of them exhibit their minima in the climate comfort zone and have these nonlinear increases outside of it where there is data coverage. So this suggests that the range is actually common across different European ranges and climates. So with temperatures then continuing to rise due to anthropogenic greenhouse gas emissions, the temperature distributions will shift, right? And now we can ask ourselves, well, what does this mean now that we have identified this climate comfort zone? And what we expect is that the number of days inside and outside the climate comfort zone is going to change. And if we abstract from other factors that might lead to changes in social media usage in general, and like the occurrence of cyber racism specifically, we can focus on how the number of racist tweets and likes might change under future temperature distributions, focusing on the temperature dependence alone. So basically we used temperature projections for multiple models and assessed the number of days warmer or colder than the climate comfort zone in 2044 to 2050 compared to 2012 to 2018. And we take the strength of the deviation from the comfort zone into account by weighting it in accordance with the previously identified temperature racist tweet response function. And the results of this process are shown in figure 3. So there's cold days on the percentage change in cold days on the left side and the percentage change of warm days on the right side. And this is shown here for shared socioeconomic pathway 585. So this is like a kind of like a business as usual scenario. However, we get similar results, even slightly less extreme for like an SSP 2.6 or something. Exactly. And what we basically see is that the response curve weighted number of days colder than the climate comfort zone decreases across all of Europe. And by contrast, the response curve weighted number of days warmer than the climate comfort zone increases in all European countries pretty much. And we find particularly strong increases in Northern and Central Europe. Now we can maybe consider that there's some sort of net effect. So like the cold days decrease, the warm days increase, maybe overall it's zero. But for most countries, the increase in response curve weighted days warmer than the climate comfort zone is significantly stronger than the decrease in cold days, especially in Northern and Central Europe. So abstracting from all other influencing factors, we could say that these countries might experience increases in the occurrence and acceptance of racist online content due to climate change. So to summarize, we found evidence that the occurrence and acceptance of racist and xenophobic tweets is non-linearly influenced by temperature, and that it is lowest for temperatures between 8 and 17 degrees Celsius, independent of the climatic zone within which the Twitter users are located. And in the future, there are more days with daily maximum temperatures outside the climate comfort zone in most European countries. And yeah, with that, thank you very much for your attention.
Thank you very much, Annika. That is a really fascinating way to end. I'd honestly never thought of that, that our grumpiness in hot conditions actually translates to some pretty unpleasant behavior, but it does really make sense. I'm going to stop sharing my screen now. And I'm going to go now to, we have a sort of slightly technical question, which I'll ask for, I'll ask Gianpaolo. And then we've got a general question, which I'll put to the rest of the group. Gianpaolo, there's a question in terms of the strategy of sort of towards climate modelling is whether we actually still really need separate models for numerical weather prediction and climate change, now that we in fact have global models running close to really fine resolutions, almost up to 1 kilometre, at least experimentally. How do you see the future of high resolution modelling?
Yes, no, great question. So in terms of the frontier of the 1 kilometer global simulation is really at the edge of what computing can do right now. So for instance, some of these exploratory simulation have been done using the top powerful supercomputer in the United States, for instance. We don't have currently this computing power in Europe, for instance. So this is the first challenge, the infrastructure to be able to run at kilometer scale globally needs to really be boosted. And then the destination Earth is first and foremost a infrastructure challenge and an infrastructure initiative to really push the computing to the level necessary to reach global kilometer scale. In terms of when models will be around this resolution, so realistically it will be a few years from now. For instance, local area models or models that are focusing on a given region will consequently be able to push much farther into resolution and also complexity. So this is not basically we sit on a graph where we have the resolution. So imagine like a TV, high resolution, high definition, and the complexity of the model. So how many processes we are able to introduce in this model. And then for the ensemble characterization, so the capacity to give a probability, then there is also the number of ensemble members. So how much granularity there is in characterizing probability. And this is really important for extreme events. So I think the 1 kilometer resolution is really a requirement if we think about CO2 and we think about emission from stocks, from industry. Those emissions are very much at local scale. So a global system which wants to provide a support for monitoring anthropogenic as well as biogenic CO2 emission needs to tap into those resolutions. And this realistically will be done a few years from now, and the satellite instrument will also be up and running for a few years from now. So there is, for instance, the European Space Agency is building a dedicated satellite called CO2M, which will be up and running in the second half of the 2020s. So that's why the modeling needs to prepare now. But yeah, I would say there are sizable technological and scientific challenges.
I think I'd agree with you there. Thank you very much, Gianpaolo. It's really, really interesting to hear ECMWF's view on that, because they are obviously very much working at this interface between weather and climate with their modelling strategies. Okay, so we have a fun question to finish with now. So do you think that it is perhaps ironic that we are talking about the impacts of climate change on a process that we know we need to stop doing to present catastrophic climate change? So what do you all think about the mitigation versus adaptation question? Who would like to jump in?
I can jump in first. I'll respond to it in terms of the context of maybe how it was asked with relation to fracking in Scotland. So yes, I think it is pretty ironic. Sort of a bit of context to it is that sort of at least in 2018, there was license blocks were owned by oil and gas companies to frack in that area of Scotland. And this research was to try and show what would the consequences be if these licenses ever do become operational. And the results of it showed by 2080 that with the water demands of fracking, rising population in Scotland, an increase in demand for water, and climate change, the water supply zones in Scotland wouldn't be resilient enough to cope with this demand. And the interest, in fact, would be even if you took the water demands of fracking out of that, they still wouldn't have the resilience to cope with limited water availability in winter, in summer, sorry, and even in winter with sort of more water available. If the population keeps on increasing and the demand for water increases at a steady rate, sort of with the current rate of population, then even without a sort of damaging technology like fracking, we would sort of be under extreme water stress. And it was to highlight the importance of sort of adapting now to try and prepare for the future and to avoid those sort of consequences.
That's great. Thank you very much, Graham. Yeah, it's absolutely water availability for pretty much any application is very much one of the things we need to adapt to, and we need to accept that some of these changes are happening, perhaps. I think we have, if someone could do something in sort of 30 seconds, we have room for, I think, maybe one or two more. So who else would like to give their
I can add my point of view. I think we should be doing both mitigation and adaptation. We should be thinking about present and future risks. And I think, as my work also shows, is that planning and development and implementation of policies and actions, they also need to aim at both vulnerability, resilience, and adaptation together, not separately. And improving all these three is possible and is definitely necessary, because both achieving short-term or medium-term and even long-term we need to achieve those in terms of political commitment, investment, and funding. And I think it's what all of us are trying to advocate here this week. Yeah, so thank you.
Absolutely. I don't know if we have room for anyone else, but I think the other point which I would add to that, taking my privilege as chair, is that that actually a lot of the measures that we have at adaptation to climate change, and particularly in where I work in Africa, actually are really helping people improve their livelihoods now, and would have been 100 years ago in the pre-industrial era. You know, people in these regions actually struggle to cope with climate variability. And I think that being able to adapt to sort of climate variability will help us with climate change, but also only has good consequences now. I'm not sure how much longer we have before we're cut off altogether, but I would like very much to thank all our speakers today, and also again directly back to the posters. Okay, so we've been told not to leave the meeting until we've been cleared. So I don't know whether we're still on